Hi, I'm Mark Barsamian. In this video, I'll be discussing counting disjoint sets using the addition rule. This material is from section 9.3 of the book, which is titled Counting Elements of Disjoint Sets with the Addition Rule. The corresponding homework is this collection of problems from section 9.3. And the topics will be the addition rule, but also what's called the difference rule and the complement rule for probability and what's called the inclusion-exclusion rule. The addition rule says this. Suppose a finite set A equals the union of k distinct mutually disjoint sets, A1, A2, up to AK. Then the number of elements in set A is simply the sum of the number of elements in each of the individual sets. The number of elements in A1 plus the number of elements in A2, all the way up to the number of elements in AK. That can be illustrated this way. So there's a picture of a set A that's made up of the union of k mutually disjoint sets. And so the total number of elements in all of set A is just simply the sum of the elements in each of those constituent sets. The next theorem is a fairly obvious one, given the addition rule. This one is called the difference rule. If A is a finite set and B is a subset of A, then the number of elements in A minus B equals the number of elements in A minus the number of elements in B. Let's draw a picture for that. Notice that if we apply the addition rule to this picture, we get this. Now, since the addition rule tells us this, if we simply subtract the number of elements in set B from both sides of this equation, we are led to that equation. So the difference rule is an immediate consequence of the addition rule. Let's go on. The formula for the probability of the complement of an event. If S is a finite sample space and A is an event in S, then the probability of A complement is 1 minus the probability of A. Now remember what that means, the complement. A complement is the sample space minus set A. It's the complement of A in this set S. Now where does this come from? Well, this is fairly straightforward as well. So let's make a picture. Now, let's think about how we would compute the probability of A complement. We see that the probability of A complement is equal to this ratio, the number of elements in A complement divided by the number of elements in S, but that can be simplified. The difference law tells us that the number of elements in A complement is equal to the number of elements in S minus the number of elements in A. And then from then on, it's just arithmetic. So let's just dive into some examples where we'll use these various theorems. Example 1 is similar to 9.1, number 17. How many strings of 8 hexadecimal digits do not have any repeated digits? Well, this might be our first example involving hexadecimal. Remember that hexadecimal is this set. It's that collection of 16 characters. So our question is, how many strings of 8 hexadecimal digits do not have any repeated digits? Well, we answer this by thinking about tasks. Let's think about populating a string of eight blanks. So we see that the total number of ways is just using the multiplication rule. The total number of ways is 518,918,400. Let's go on. Question B. How many strings of 8 hexadecimal digits have at least one repeated digit? Now, if you think about that, counting that directly would be very confusing. We'd have to count the number of strings that have exactly one repeated digit, the number of strings that have 2 repeated digits, maybe one repeated number 3 and one repeated number 7, or maybe a 3 repeated twice, or maybe a 3 repeated 5 times and a 7 repeated just twice. There are all sorts of combinations of different kinds of strings where there's at least one repeated digit. But this is where the difference rule is handy. What we should do is we should count the total number of strings of 8 hexadecimal digits where repeating is allowed, and then subtract the number of strings that don't have any repeats. This might be clear if I introduce some symbols. So there I've introduced symbols. Set S is the set of all strings of 8 hexadecimal digits. Set A is the set that have no repeated digits. And then the set S minus A would be the set that have at least one repeated digit. So this is what we want to count. We're interested in that set. So the number of elements in that set we're going to compute using the subtraction rule, the difference rule. Now notice that we counted set A in question A. So what we need to do is we need to count set S. We need to count the number of strings of 8 hexadecimal digits. Well, let's think of this as tasks. We have 8 blanks to fill. So task 1 is to fill blank 1, task 2 is to fill blank 2, all the way down to task 8, which is to fill blank 8. So the total number of ways is just 16 raised to the 8th power. So that's the crazy big number. That's the number of elements in set S. So what we need to compute now is the difference, the number of elements in set S minus the number of elements in set A. So I'm going to subtract the number from question A from the number that we just found. And the result is that crazy big number. Let's go on. Question C. What's the probability that a randomly chosen string of 8 hex digits has at least one repeated digit? Well, that's going to be obtained by the equal probability rule. The event that we are interested in is this event, S minus A. That's the thing that we just counted. So the probability of S minus A will be the ratio. The ratio of the number of elements in the set S minus A divided by the number of elements in set S. Well, those numbers are sitting on the previous page. There's the number of elements in S minus A. There's the number of elements in set S. When we divide, we get the following. We end up with a probability of roughly 0.879. Let's go on. Example 2. This one's similar to 9.1 number 7. A password must be from 4 to 6 symbols long and may include these symbols: uppercase letters, lowercase letters, and digits. Question A. How many passwords are available if repetition is allowed? Well, this is going to be a problem that involves using the multiplication rule to choose symbols to go in blanks. But the problem is also going to involve the addition rule, because we are going to have to count 3 different batches of passwords. So we introduce letters for these 3 collections of passwords that we're interested in. We're interested in passwords that have 4 characters, or 5 characters, or 6 characters. Notice that those 3 sets are disjoint. So what we are interested in counting is their union, A union B union C. And by the addition rule, since those sets are disjoint, we can count each set individually and add them up. So how many passwords are in set A? Passwords with 4 characters. Now let's see. How many characters do we get to choose from? There are 26 uppercase letters, 26 lowercase letters, and 10 digits. So that means that there are 62 total characters to choose from. So the number of elements in set A is just going to be 62 to the 4th, because I get to choose the character for the first blank, that's 62 choices, then choose a character for the second blank, that's 62 choices again, and so forth. The number of elements in set B is going to be 62 to the 5th, and the number of elements in set C is going to be 62 to the 6th. If you type this into a computer, you get the following. This crazy big number of passwords available if repetition is allowed. Let's go on. Question B. How many passwords have no repeated symbol? Well, then let's introduce symbols for this case as well. Now we're interested in passwords that are 4 characters long, or 5 characters long, or 6 characters long, but with no repeated symbols. So let's use very similar symbols to what we had before. So there are our 3 sets that we are interested in. Passwords with 4, 5, or 6 characters and no repeated characters. Well, those are disjoint sets. So by the addition rule, the number of elements in their union is just the sum of the number of elements in each of the 3 sets. So the number of elements in the union is just the sum of the number of elements in each of those 3 sets. Now these we can figure out in terms of tasks. To choose a password with 4 characters, we get to choose any of the 62 characters for the first blank. But for the second blank, we can't choose whatever character we already chose for the first blank, so we only get 61 choices for the second blank, and so forth. So that's the number of elements in set D. That's the number of elements in set E. I got to choose 5 characters with no repeats. And then finally, the number of elements in set F. So when I add these up, I get the following. That's the number of passwords that have no repeated symbol. Let's go on. How many passwords have at least 1 repeated symbol? Now, if you think about this, the passwords that have at least 1 repeated symbol are simply the set of all passwords minus the passwords with no repeats. Now here I should make clear, we're talking about passwords of length 4, 5, or 6. Now think about this. These sets are sets that we dealt with in questions A and B. And in fact, this first set is A union B union C. That's the set of passwords of length 4, 5, or 6 characters where repetition is allowed. And notice that we counted that set in question A, and we got that number of elements for that set. The passwords with no repeats, we counted in question B. That was the set denoted D union E union F. So we're interested in counting this set, and so by the difference rule, we can count this set and subtract the count of this set. So that's the number of passwords with at least one repeated symbol, 12 billion and so on. Question D, what's the probability that a randomly selected password has at least one repeated symbol? And again, here we're talking about passwords of length 4, 5, or 6. Well, that's going to be, by the equal probability rule, just the number of those passwords that have at least one repeated symbol divided by the number of all passwords. So the probability is roughly 0.22, roughly a 1 in 5 chance that if you choose a randomly selected password of 4 or 5 or 6 hexadecimal characters, you will get one that has at least one repeated symbol. Let's go on. Example 3. This one's similar to 9.1, number 22. Consider strings of length n over the alphabet A, B, C, D, E. Question A is, how many strings contain at least one pair of adjacent characters that are the same? Well, let's define some sets here. Let's define set S to be the set of all strings of length n over that alphabet. Now, to say that we have a string over the alphabet means that we have a string made up of characters chosen from that set. So that's the set of all strings, set S. Let's let set A be the set of strings of length n that have no pair of adjacent characters the same. Now we are interested in the set of strings that contain at least one pair. So that means that we are interested in the set S minus A. In fact, we're being asked to find the number of strings in set S minus A. So by the difference rule, we need to do this by finding the number of elements in set S and subtracting the number of elements in set A. We'll do that on the next page. Now, to find the number of elements in set S, we have to consider these tasks. We have to build a string of length n using the letters from the set A, B, C, D, E. We see that by the multiplication rule, the number of elements in set S is 5 to the n. Now, set S is a set of all strings of length n. We have any kind of repetition allowed there. Now we need to count set A. Remember, the set A is the set of strings that have no pairs of adjacent characters the same. So we'll do that on a page below. So to count the number of elements in set A, we're going to be considering choosing letters to fill up these blanks. Now, to fill up the very first blank on the left, we get to choose any letter that we want. So there are 5 different letters we can choose from for that blank. Now what about the next blank? How many ways can we choose the letter that goes in this blank? Well, we just have to make sure that it's not the same letter that's sitting here. So whatever letter was chosen for blank 1 can't be the same letter for blank 2. So N2 is the number 4. Now here's where it gets interesting. Consider filling the third blank. Now in the past, when we've counted strings, we've often discussed strings where no repetition is allowed. And in that case, we would put the number 3 in this spot. But the thing is, all that we have to make sure that we don't allow is we don't allow the same letter to go here that was used here. We don't care if the same letter that was in blank 1 goes into blank 3. We just care that these two adjacent letters are not the same. So the number of ways that we can fill blank 3 is, again, the number 4. We just have to not choose the same letter that was used to fill blank number 2. So we keep going this way for all the blanks until the end. Each blank, there are 4 ways to fill it. We just have to make sure in each case that we don't put the letter in that was already used in the blank immediately to the left of a particular blank. So the total number of ways is the following. The total number of ways is 5 times 4 to the n minus 1. So that's the total number of strings where there is no pair of adjacent characters that's the same. Now, in the previous page, we forgot to label our result. So in the previous page, we found that the total number of strings of length n was 5 to the n. In the current page, we found the total number of strings of length n where there are no adjacent characters of the same is this number, and that's that quantity, n parentheses a. So now we need to compute the thing that we're being asked for. We'll do that on the next page. So the result is the number of strings where there is at least one pair of adjacent characters that are the same is this number, 5 to the n minus 5 times 4 to the n minus 1. Question B. If a string of length 7 over this alphabet is chosen at random, what's the probability that it contains at least one pair of adjacent characters that are the same? Well, that probability is going to be the number of strings of that length of that type divided by the total number of strings of length 7. So this number we counted on the previous page. This number we counted 2 pages ago. Those are the expressions we got on the previous pages. But in our current problem, the length is 7. So the probability is 0.737856. Notice that I did a lot of simplifying. It was just kind of fun to do this. 5 over 5 to the 7th is 5 to the 6th. And then we've got 4 to the 6th over 5 to the 6th, so that's just 4/5 to the 6th. So this can be simplified quite a bit. Let's go on. Example 4. 7 people, denoted by letters A, B, C, D, E, F, G, are seated randomly in 7 seats in a row. What's the probability that A and B are not seated together? Well, what we should do is count the number of seatings that are possible with 7 people, and then count the number of seatings where A and B are seated together. Now, the word that we want to use here is permutations. We're interested in the number of arrangements of 7 people in 7 seats. So that is, we're interested in the number of permutations. So we'll let S be the set of permutations of the set, A, B, C, D, E, F, G, and let A be the set of permutations that have A and B seated together. And so what we're interested in is the set S minus A. And we're being asked for the probability of that. And so that's the probability of A complement. And we can use the complement rule. So we need to count the number of permutations of the set, and then count the number of permutations that have A and B seated together. That's set A. And then we need to construct this quantity, and that'll be our probability. Well, the total number of permutations is easy. So it's the number of permutations is just 7 factorial. We have 7 seats to fill. We can choose any of the 7 people to go in the first seat, any of the 6 remaining people for the second seat, any of the 5 remaining people for the third seat, and so forth. So that's pretty straightforward. Now it gets a little bit trickier to count the set A, the permutations that have A and B seated together. Now this problem appears in this section 9.3, which is about the addition rule. So I'm going to solve this counting of set A using the addition rule, but then I'm also going to count it using just rules from previous sections of the book. So I'm going to do this on the next page. We're interested in seatings where A and B are together, and we can express this as the union of 2 different sets of seatings. If we let set B be the seatings with A and B together, but A on the left, and let C be the seatings with A and B together, but with B on the left, then we see that the set A is the union of sets B and C, and it's a disjoint union. None of the seatings of type capital B are in the set of seatings of type capital C. So the number of elements in set A is the number of elements in set B plus the number of elements in set C. So that's the solution that the book has in mind when they put this problem in section 9.3 of the book, which is about the addition rule. We would solve this problem by counting the number of elements in set B and the number of elements in set C, and add them up to get the number of elements in set A. Well, let's do that. To count the seatings of type capital B, we have to think about tasks. So our first task is going to be to choose the seat for person A. So the number of ways that we can do that task is 6, because person A can only sit in one of these 6 seats. Person A can't sit here because person B is going to have to be to the right of them. Then what's our next task? Well, we choose a seat for B, but the number of ways of doing that is just 1, because B has to be immediately to the right of A. Now what's our third task? Our third task is, well, we've got A and B sitting together somewhere in 2 seats. Maybe it's those 2 seats, maybe it's these 2 seats, we don't know. But wherever it is, there are 5 remaining seats that need to be filled. So we could just think of filling those 5 remaining seats from left to right. So our task 3 will be fill the leftmost empty seat. There are 5 ways of filling that seat, because there are 5 letters left to go into seats. And then we're going to choose the letter for the next seat, and so on. So we see that the total number of ways is just 6 factorial. Now we need to count the number of seedings with A and B together and B on the left. Well, that's going to be the exact same thing, just putting A in a seat first. And so it's just going to be the same result. We'll do that on the next page. So the number of elements in set C is 6 factorial as well. So the number of elements in set A is 2 times 6 factorial. Now, let's remember what we're going to do with this. A while ago, we found the number of elements in set S was this. Now, we are interested in the probability of this set. The probability that A and B are not seated together, that's the probability of A complement, and that was going to be computed using the difference rule. 1 minus the number of elements in set A divided by the number of elements in set S. We see the probability is roughly 0.714. Now I said that I was going to solve this problem two ways. I think I won't. In the interest of time, let's go on. Example 5 is similar to 9.3 number 9, counting iterations of a loop. So we're supposed to consider the following algorithm segment. For I going from 1 to 1,000, and for j going from 1 to I, do all the statements in the body of the loop. So you for a particular value of I and a value of j, the statements in the loop get performed, and then j gets incremented to the next value of j, and the statements in the loop get performed again. And then j gets incremented again, all the way until j equals the number of I. And then I gets incremented to the next value, and we start the whole thing again. So the question is, how many times will the innermost loop be iterated when the algorithm segment is run? So how do we approach this problem? Well, think about this. The loop gets iterated for every pair of this form. So the loop gets iterated once for every pair of the form I comma j, where I is in this range and j is in this range. Well, that collection of all those pairs is the collection that we need to count. We need to count all those pairs. Now, we could express the set of all such pairs as a union. We'll do that on the next page. So there's our union of the set of all pairs. The pairs with I equals 1, denoted that way. The set of pairs with I equal 2, denoted that way, and so on, all the way up to the pairs with I equals 1,000. Now notice that this is the disjoint union. None of the pairs that have I equals 1 are in any of the other sets. The left element of the pair is the number 1. That distinguishes the batch of pairs. So this is a disjoint union. So by the addition rule, since this is a disjoint union, the number of elements in set A is the sum of the numbers of elements in all those other sets. So the question is, how many elements are in those sets? Well, remember, this is the number of pairs with I equals 1. Well, what are the pairs that have I equals 1? Those pairs have to have j be greater than or equal to 1 and less than or equal to I. In other words, j can only be the number 1. Now what about the pairs of that form, pairs with I equals 2? Well, those pairs, I is the number 2, and j has to be greater than or equal to 1 and less than or equal to 2. So j can be 1 or 2. What about the number of pairs with I equals 3? Well, for those pairs, j can be 1 or 2 or 3. So that means that there are 3 pairs of that form. And so forth. All the way up to the number of pairs with I equals 1,000 is 1,000. Because j has to be greater than or equal to 1 and less than or equal to 1,000. There are 1,000 different choices for j. So there we go. That's the sum. Hey, look, that's the sum of the first 1,000 positive integers. That's a blast from the past, from early in the course. We know that there's a formula for this. 1,000 times 1,000 plus 1 over 2. So the answer is 500,500. Now there's one more new topic for this homework assignment. It's called the Inclusion-exclusion rule. Now before discussing this rule, let's go back to the beginning. Remember the addition rule. It says if you have a set that's a union of disjoint sets, then the number of elements in the big set is equal to the sum of the elements in all the constituent sets. Those are non-overlapping sets. Those are disjoint sets. Now, we're going to consider now the situation where sets are not necessarily disjoint. So we have a union of A and B, where A and B are not necessarily disjoint. So we want to count the number of elements in the union. That's not going to be just the number of elements in A plus the number of elements in B, because if you think about it, if A is this region on the left and I color it green, and B is the region on the right and I color it red, if I count the number of elements in A and the number of elements in B, then I've counted this collection of elements twice. So if I want to find the number of elements in this union, I need to count the number of elements in A and the number of elements in B, and also count the number of elements in this intersection. And I need to compute the number of elements in A plus the number of elements in B minus the number of elements in that intersection, so that they're not counted twice. And a similar thing happens for 3 sets. Now there's an inclusion-exclusion rule for 3 sets, where we're going to be counting sets that could be configured like this. And the rule for counting the union, A union B union C, is this big formula. Now, I'm not going to go through that. It's the same idea of this. When you count the individual sets A and B and C, you end up overcounting some of the overlapping regions. So these regions where the sets overlap get counted 2 or maybe even 3 times. So you correct for that overcounting by having these terms where you subtract the counts of some of the intersections. So like I said, I won't go over that formula and why it works. Now this concept is used in the solution to homework problems number 24 and 34 on homework set 9.3. Those 2 problems. Now book examples 9.3 number 1, 6, and 7 discuss almost identical problems. Because of that, I won't present similar examples in this video. So we'll stop